Hi everyone, welcome to video number 3 for Module 8, in which we're talking about models with a single categorical predictor. In today's video, we're going to be expanding on our previous discussion to think about situations in which we have more than two levels to our categorical factor. Right, so in previous videos, we talked about situations in which we have two groups. Right, so we have two levels, such as a control group and an experimental group in our factor, and we can make a comparison between those independent samples. In this video, we're going to talk about situations in which we have more than two groups and how we can use the same principles of treatment coding and contrast coding to address questions about group differences when we have more than two groups. So to start with, we're going to have a continuous relationship, and then we're going to break it apart and turn it into more discrete relationships. So as we said in the previous videos, that's generally a bad idea. If you have a continuous variable, you want to keep it continuous. But in this case, we're going to do it because we want this to be sort of an illustrative example. So we're looking at the relationship between VO2 max and time in the 800-meter sprint in 21 track and field athletes. And as you can see, there's a negative relationship between VO2 max and 800-meter sprint times, which is actually best represented by this dotted red line, which is the coefficients from this formula here. So this red line has an intercept of 112.89 and a slope of negative 0.37. So for every 1 second slower you run the 800 meters, your estimated VO2 max goes down by 0.37 milliliters per kilogram per minute. Both the slope and the intercept are statistically significant in this model, and ultimately we would conclude that there is a strong negative relationship between a person's 800-meter dash time and their VO2 max. And this would be using simple linear regression, as we've looked at in previous chapters. However, right, we could also look at this in a slightly different way and turn our continuous variable into a categorical factor. So we're going to take our runners who all had times on the 800-meter dash, right? And we're going to turn them into two different groups, right? So we're going to make this categorical and discrete rather than continuous. So we're creating a new variable called faster, where we take our 11 fastest people, they all get a 1, and our 10 slowest people, they all get a 0. Now this doesn't quite divide evenly in half because we have 21 people, but we can create these two groups even though they have slightly uneven numbers. If we plot these data in a slightly different format here, now we're using box and whisker plots to represent the distribution of the people in the faster group and the people in the slower group. You can see that the faster group generally has higher VO2 maxes than the slower group, but there is some overlap between these two different distributions. We can still use a general linear model, right, to draw a line through these data points, right? And we know that that line is going to hit the mean of the faster group and it's going to hit the mean of the slower group. So if we had, for instance, coded slower as 0 and faster as 1, this is the best fit line that we would get. It would have an intercept of 59.225, which is the mean of the slower group in this case, plus 6.707 times whether you were in the slow group or the fast group, right? And if you're in the slow group, this is a 0, so this times 0 becomes 0, and you're left with 59.225, right, which is the mean of this group. If you're in the faster group, this is a 1, so you have 1 times 6.707, which would be plus 59.225, and the mean of the faster group is 6.707 milliliters per kilogram per minute higher than the mean of the slower group. And is that a statistically significant difference? Well, if we actually ran a model using these codes, this is what we would get, right? So again, here is our intercept and here is our slope. And you can see that there is a statistically significant effect of the slope. So people in the faster group had a higher VO2 max, or I should say we would infer that people who run the 800-meter dash faster have a higher VO2 max than people who run the 800-meter dash more slowly. Now, what if we change the way in which we are coding slower and faster, right? So we can change this from being faster with 1s and 0s to faster.c with 1s and negative 1s. So our faster group still gets a 1, but now rather than a 0, our slower group is going to get a negative 1. So now rather than treatment coding, right, we are contrast coding these two variables, but what we're still going to end up with from our general linear model is a line that runs through the mean of this group and through the mean of this group. However, because we've changed what the x variable is, we now get a different slope and a different intercept, right? So if slower is coded as -1 and faster is coded as 1, our model is now 62.578 plus 3.353 times whether you were faster, right, and you get a +1 here, or whether you were slower and you get a -1 here. So before we go forward, take a second to pause this and answer for yourself, what is 62.578 and what is 3.353? How does these things relate to the means of these two different groups? Okay. So when we get this regression equation, right, because we have changed what the coding is on this x-axis, 52.578 is the value of y when x is 0, and x is 0 between our two groups. So 62.578 is actually the mean of our two group means, right? It is the value when x is 0, which is on average between the faster group and the slower group. So that's the mean of the group means. Then the difference of 3.353 is actually half of the difference between the group means, right? So we can see that if we plot the group means here, 3.353 is how we would get from the mean of means to the mean of the faster group, right? We would add 3.53 to 62.578 to get 63.5931 or 65.5931, right? And we would take 62.578 minus 3.353 to get 59.225. So each of these means is 3.353 away from the intercept, and the corollary of that is that these means are then double this amount away from each other, right? Because again, the slope is always the change in y for a 1 unit change in x. So if I go from the mean of the faster group and I change 1 unit, right, I've gotten to 0. I've gone down 3.353 in order to get to the intercept. And if I make another 1 unit change, I go down another 3.353 to get to the mean of the slower group. Right, so this is how we would represent or interpret the intercept and the slope in a situation in which we have contrast-coded predictors. But what if we wanted to break this out into more than two groups, right? What if we actually wanted a situation in which we don't want to represent it continuously, but maybe we wanted to look at 3 different groups, right? We wanted fast people, slow people, and people who are kind of in the middle, right? You could go even higher, but we'll start with 3 groups for now because I think that's a pretty useful example. And the same general linear modeling principles and contrast coding principles that we have used before still apply in this situation. So when we're talking about a categorical general linear model, right, with 3 groups, we have to think carefully about how do we actually want to represent those 3 groups numerically. We could say, oh, well, maybe I'll code this as 0, 1, and 2, or I'll code it as -1, 0, and 1. The problem is, though, we can't use a single code when we have 3 levels, because a 1 unit change in x always has to mean the same thing. When we only have 2 levels, that's all right because I'm going from one group to the other group, so a 1 unit change in x can just be the difference between the group means. However, when I have more than 2 groups, now unless all my groups are exactly the same distance apart, right, a 1 unit change in x doesn't mean the same thing. The change from 0 to 1 here is bigger than the change from 1 to 2. Right? Or the change from -1 to 0 here is bigger than the change from 0 to 1. So we can't represent all 3 means on one scale because a 1 unit change in x doesn't create the identical change in y because the groups are different distances apart. So in order to represent these variables, we actually need multiple codes in order to successfully code more than 2 groups in our general linear model. And strictly speaking, we need a number of codes equal to our number of groups minus 1, which is something we'll talk about more and work on more in the lab. But in this case, we have 3 groups, so we're going to need 2 codes in order to represent all of these means. So by default, R likes to use dummy codes or treatment codes, right, to represent these groups. So it'll create one lambda, right, in which the faster group is coded as 0, the medium group is coded as 1, and the slower group is coded as 0. And then it will create a second lambda in which the faster group is coded as 0, the medium group is coded as 0, and the slower group is coded as 1. So what would a 1 unit change mean for these codes? Well, the answer is that it's slightly different depending on which code you're in, right? Because in both of these codes, the faster group is treated as 0. So if you have, and in our model, we're going to have to enter values for both of these codes. So if I enter 0 for both of them, right, then I have somebody who is in the faster group. If I have a 1 and a 0, then I have someone who's in the medium group. If I have a 0 and a 1, then I have somebody who's in the slower group. So our intercept, right, when both values are 0, our intercept will refer to the faster group. And then when we have a 1 and a 0, that will be the difference between our faster group and the medium group. And if I have a 0 and a 1, that'll be the difference between the faster group and the slower group. And we'll show you a little bit more about how that works before we move on to thinking about this as a contrast code. Okay, so here's our output from R if we fed in these different treatment codes. And you can see that we have an intercept of 68.5. We have this variable which it calls groups medium because it takes the name of the level that's being compared. Groups was the name of our variable. Medium is the name of the level. And you can see we have a slope of negative 6.75. And then we have groups slower. So again, groups was the name of the variable. Slower is the name of the level. It has negative 10.536. So this is our intercept, right? This is the slope for our first code. And then this is the slope for our second code. And so what we have then is an equation where we can actually solve to get these group means that we see down here. So the first code, right, the slope for the first code tells us about the difference between the intercept, 68.5, which is the mean of the fast group, and the mean of the medium group, which is 6.75 points lower than the fast group, right? So we go down 6.75 points to get a mean of 61.75. Similarly, the second slope, right, tells us about the comparison between the intercept, which is the mean of the faster group, and the mean of the slower group, which is 10.536 points below the faster group, right? So to calculate this, we have our intercept of 68.5. If you're in the slower group, this negative 6.75 is getting multiplied by 0, so it goes away. Negative 10.536 is getting multiplied by 1. So we have 68.5 minus 10.536. That leaves us with 57.69, which is the mean of the slow group. So these treatment codes successfully generate predictions that are the means of our three different groups. However, right, as we talked about when we were doing two levels of a factor, we don't always want to use treatment codes. There's some computational reasons and some interpretational reasons why we might actually prefer contrast codes. So we're going to walk through an example now using contrast codes for this variable. And contrast codes get a little bit trickier, right? But they still follow the same basic rules as contrast codes. So we're going to create two different codes, right? Because again, we need codes equal to our number of groups minus 1. So we need two codes to generate the means of these three different groups. And in this case, we're going to have a linear code and a quadratic code, right? So one code is going to sort of have a linear, a flat line. The other code is going to sort of allow for a bit of a curve, a bend in the line, and we'll visualize that in a little bit more detail later. But the first thing to think about is just, are these actually contrast codes? And remember, the sum of the levels has to be 0. So for our linear code, we have 1 plus 0 plus negative 1, so that's 0. And for our quadratic code, we have negative 1, 2, and negative 1, so that also sums to 0. So both of these are indeed contrast codes. And we can represent then the mean of our three groups using these two orthogonal contrast codes. So if I actually plug those values into R, so now I get a regression equation that looks like this. Rather than treatment codes that tell me exactly which group you're in, I have contrast codes, right, that assign values of 1, 0, and -1 for the linear code, or -1, 2, and -1 for the quadratic code. And you can see now our coefficients have changed pretty substantially. We have to now ask, well, what does this intercept actually represent? The value of the intercept has changed. It's no longer the mean of the FAST group, but it's 62.7381. And the other thing that we could see is that the values of those slopes have changed, and specifically, this second predictor is now no longer statistically significant. When this was a treatment code telling us about the difference between the fast group and the slow group, it was statistically significant. Now with this quadratic predictor, it is not. So why is this effect not statistically significant in this situation? Well, what we can do first is visualize some of these results to have a better understanding of what they actually mean. So if we zoom in on the linear code for a second, recall that faster was coded as +1, the medium group was coded as 0, and the slower group was coded as -1. So what we're asking is there a increase, right, across these groups as we go? So we're trying to draw a line through essentially these different groups, and we're saying, is there a linear effect? Does it change as we go from -1 to 0 to +1? And now it doesn't have to change exactly in the overall model, right? We're going to be able to estimate exactly the mean for each group. But in this code, what this allows us to compare then is just a linear tendency in these data, which then gets modified by our quadratic variable when we pull them all together. So this linear code won't tell us exactly, the mean of any of these groups on its own. It has to work together with the quadratic code in order to generate those predictions. But the linear code is asking, is there a roughly linear change in these data? And it looks like there is. Now the quadratic code, right, recall, is where we have groups coded as -1 for both the faster group and the slower group, and 2 for the medium group. So we're asking, is there any sort of bend in this code? Or more specifically, is the medium group different from the average of the faster and the slower groups? Because these two things are coded with exactly the same value in the quadratic code, so they're effectively getting averaged together. We're treating them as the same group. -1 applies to both the faster group and the slower group. So the quadratic code is asking, is the medium group different from the combined faster and slower group? And if it's not, this isn't going to be statistically significant. And because the medium group falls somewhere in the middle, right, of the faster and the slower group in this instance, this quadratic code is not statistically significant because this isn't statistically different from the average of these two groups. And if we actually walk through the math and add these different things together, we can actually show how if we take the intercept plus the linear code times, or the slope times the linear contrast, plus this slope times the quadratic contrast, we actually get exactly the same means that we got out of the treatment coded variable. So the model's a little more complicated, I would say, in terms of the way these codes are actually built and what they represent, but it gives us some excellent improvements in terms of the efficiency of kind of computing these estimates if we had to do it by hand. And also it gives us some improvements in the interpretability, because now this intercept is when these x's are 0, right? So when our linear code, x is 0 in the medium group, right? And in the quadratic code, x is 0 between all the groups, right? So when all x's are 0, what we're effectively asking then is on average across all of the data, right? The linear code is asking about this change across all three groups. So at the 0 point, right, we're somewhere in the middle of this line. The quadratic code is asking about the bend in this line. And so it's going to generate a number, right, when all x's are 0, that is sort of in the middle of all the parts of our data. We're asking on average across all groups, what is the VO2 max? And then we can actually solve for the individual differences using these two contrasts here, which will generate the means of both of our different groups. Or sorry, of all three of our different groups. The other thing we want to take a look at is that although we get very different estimates in our coefficients here, we actually get identical results in the omnibus test at the bottom of the R output, right? So you can see that our intercept, our two slopes, and their statistical significance is different if we use treatment codes than if we use contrast codes. However, the R squared, right, the F, the omnibus F, and the p-value are exactly the same across each of these two groups. And again, the reason for that is that both sets of codes are predicting the mean of each group. So even though they do it in slightly different ways, whether we use the treatment code or whether we use the contrast code, we're ultimately getting the exact same predictions out of this model, which means we're getting the same sums of squared errors, which means the pre, the R squared, and the F values are all going to be the same. Okay, so we're going to walk through that in a little more detail in the next video, but I think that's an important thing to keep in mind when you're looking at these different models. And again, treatment codes and contrast codes both work equally well in terms of being statistically valid, right? They're going to give us the same predictions, which means they're going to give us the same sums of squared errors, which means they're going to give us the same omnibus F results. However, they are going to give us very different coefficients, and the statistical significance of those coefficients will change depending on how we've coded the variables in our model. So we have to pay careful attention to what variables we're actually putting into our regression model and the effect that that has on the interpretation of the statistical output.